This is the sun. I assume you guys have seen the sun before. What we're going to be mainly talking about today is the structure of the sun, all the different parts of the sun. And we're going to start with how the sun makes light, okay? Does anybody happen to know what process the sun uses to make light? The sun is not on fire, okay? So does anybody know how the sun makes light? This is kind of I'm not sure if anybody will know this one, but let's see if anybody does. Let's check this out. See, somebody's giving an attempt right now. Ooh, we're getting some attempts. Yeah, Okay, that is correct. That is correct. The sun makes light through a process called fusion. Okay? Fusion. Sometimes called nuclear fusion. So this is somewhat related to the way that we make power in a nuclear power plant, but it's not exactly the same thing. Because what we do in a nuclear power plant is something called fission, okay? Fission. The sun uses fusion, and we, in a nuclear power plant, use fission. You may have heard that nuclear power plants split atoms. So fission is when you take a very large atom and you split it into smaller atoms. So if you had one big one, fission is to do this. That's fission. So can anybody figure out what fusion is? Does anybody know what fusion is? Hint, it's related to fission. So see if you can figure it out. If fission is splitting a larger atom into two smaller ones, yeah, fusion is taking two smaller atoms and sticking them together. Okay, so fusion and fission are basically opposites of each other. Actually, I have a slide right here. So this is fission. You take this big one and split it into two. That's what we do in nuclear power plants. The sun is taking small atoms and sticking them together through fusion to make bigger atoms. Okay? So that's what the sun is doing. Now, if you read the history of the solar system, which, hint, hint, you probably should, it's posted up on Canvas, we know that in order for fusion to happen, like the gas in this room right now is not fusing. If it was, I would be dead. And that's because the air in this room is not in the right conditions for fusion to naturally happen. Again, if you read that file, you know that in order for fusion to happen naturally, just on its own, then you need the density to be extremely high of whatever gas you're dealing with, and you need the temperature to be extremely high. So there's only one part of the sun that has a high enough temperature and a high enough density to bring these atoms together to make the fusion happen. Does anybody know what part of the sun would you expect this fusion to be happening if it has to be the hottest part of the sun and the densest part of the sun? That's correct. It's the core. So what we're talking about, the place where you can think of the power plant of the sun being, is deep down in the center of the sun where you can't actually see. There's too much gas in the way for us to actually see the fusion happening, okay? So we'll talk a little bit later about how we know that the fusion is actually happening. But for now, we're talking about the core of the sun. The core uses fusion. If you're going to be using fusion, you're going to have to fuse small elements together. Can anybody figure out what element the sun is probably fusing together? It needs to be very small, and there needs to be a whole ton of it. That's correct. That's correct. The sun is fusing hydrogen, okay? So the sun's process that generates light is hydrogen fusion, okay? There's a whole ton of hydrogen in the sun. The sun's 75% hydrogen, give or take. And hydrogen's really small, so that's what's going to fuse. So what I'm going to do is I'm going to bring up the dot cam that the school let me borrow. And what we're going to do is I'm going to show you the details of this hydrogen fusion and why it makes light, okay? So check this out. Let me just change my window here. Here we go. Okay, now this right here, I'm going to go ahead and tell you, this is going to be the most technical thing that that we're probably going to talk about the entire semester. It's going to look really complicated, but after we draw it all out, I'm going to simplify it down into a much more compact, simple way of thinking about it. So let's work our way up to it. Now, there are actually a lot of different ways to fuse hydrogen, but the sun uses one particular process most of the time. And that particular type of hydrogen fusion is called the proton-proton chain. Proton-proton chain. Now, let me zoom in a little bit. Now, why do we call it the proton-proton chain? Well, remember, the temperature is extremely, extremely, extremely hot in the center of the sun. And one thing that we haven't talked about yet that tends to happen, when you're in these kind of, million degrees situations, remember, temperature is a measure of the jiggles in a substance, so the hotter something is, the more it jiggles. And essentially what happens is if you get some atoms in a place that's as hot as the center of the sun, the electrons that are attached are so fast moving, they get so much energy that they essentially pop off of the atoms. So that means that all of the atoms I'm about to tell you about in this picture, in this process, have lost all of their electrons, okay? And technically, there's a name for atoms that are missing electrons, and it starts with an I. It's a very short word. Does anybody know what this word is? Does anybody know what we call atoms that are missing their electrons here? Ions. Ions. Yes, these are called ions. And so technically, this type of gas that's in the center of the sun here is called a plasma because it's made out of ionic atoms. These atoms are missing their electrons here, okay? So let's keep that in mind. If we had a hydrogen atom and it lost all of its electrons, what's the only thing left in that hydrogen atom? What's the only thing left in the nucleus of that hydrogen atom if the electrons are gone? Yeah, a single proton. Somebody said neutrons too. Regular run-of-the-mill hydrogen doesn't actually have any neutrons. You can have neutrons in hydrogen, but the type of hydrogen that we normally think of, the abundant common kind, is just proton. Just one single proton. So that means a single proton by itself is a hydrogen atom. It's just an ion because it's missing its electrons. So every single solitary proton by itself is also a hydrogen atom, okay? So that's why it's called the proton-proton chain, because we're sticking together hydrogen atoms. We're sticking together protons, okay? So in this particular type of fusion, the sun starts with 4 atoms of hydrogen. So I'm going to draw that right here. There we go. That's our 4 atoms of hydrogen. And I'm going to put a plus on them. because that's our protons, right? So that proton is a hydrogen atom, that proton's a hydrogen atom, that proton's a hydrogen atom, and that proton's a hydrogen atom. Just so that we remember that they're hydrogen atoms, I'm also going to draw a little letter H, capital H next to them. That's the symbol for hydrogen. Okay, now we're going to fuse them, which means because it's so hot and so dense, they're going to come together and stick, okay? They're going to come together and stick. They don't want to, but because it's so hot and so dense, they accidentally run into each other, and the strong force is able to stick them together, okay? So let's bring them together like this. Okay, that's them fusing. Okay, and so if we stuck together 4 protons, we're going to have 4 little balls stuck together right here. Let me zoom in a little bit. There we go. So we stuck together these 4 protons, and so we have a new atom right here made of 4 balls. Now, don't overthink this. How many of these little balls should have pluses on them? How many? Don't draw anything yet, but how many of these balls should have pluses on them? Should. Don't overthink it. And my document cam froze up, so give me 1 second. I need to reboot it while you guys are answering that question. There we go. Yeah, we would expect all 4 to have pluses on them because we had 4 balls with pluses. We had 4 protons coming together. So now it seems like we would just have 4 protons stuck together. But it turns out when you fuse atoms, sometimes funny business happens. And in the proton-proton chain, we get a little bit of that funny business. It turns out when you stick them together, 2 of those protons lose their charge. Okay? 2 of those protons lose their charge. That's not something that just happens like in this room right here, or in your room, wherever you're at. But it does happen in fusion sometimes. So that means if those protons lost their charge, what did those protons turn into because of that fusion? The 2 protons that lost their charge turned into 2 somethings. What did they turn into? Yes, that's correct. That's correct. They turned into neutrons, okay? They turned into neutrons. Again, that's not something that normally happens. So that switching there as part of this fusion causes some other particles to pop out of this atom, okay? Some other particles are going to pop out of this atom. So we made a new atom, but we also, here we go, we're going to get 2 photons. That's 2 beams, like 2 little particles of light right there I'm drawing. 2 photons pop out. And these are going to be extremely high energy photons. What is the highest energy kind of light? What kind of photons are we making right here? The absolute highest energy kind of light. That's correct. That's correct. These are gamma ray photons, okay? So these are gamma ray photons. So I'm going to put the word gamma here. Gamma, gamma. And the symbol for gamma rays is this. Looks like a fish swimming down, like this. That's just the Greek letter gamma. So that just stands for gamma ray. So when we make this new atom, it releases some high energy light, okay? But that's not done. It also produces 2 other weird kinds of particles. So here we go. Popping out also are 2 neutrinos. And I'll explain what these are in a second. This is not the same thing as neutrons. It's a totally different thing. 2 neutrinos pop out, And at the same time, I'm going to put these down here. Here we go. Put two little pluses on these. Two positrons. Okay. Like I said, this is a nasty looking diagram right here, but it's almost done. Okay, so let's check this out. Again, we fuse 4 atoms of hydrogen together, and we make a new atom, and at the same time, all of this stuff pops out of that atom because of the monkey business that was happening during that fusion. Okay, we know what gamma rays are. Let's talk about what these other things are. Neutrinos. Neutrinos are really, 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 really weird. Like, let's say that I was walking along next to you, like a couple of feet away from you, because I'm not obeying the social distance guidelines. Oh no, I got too close to you with my baseball, and you're like, what's going on, dude? And then I just, in response to you, I just take my baseball and I chuck it as hard as I can right at your face. If I baseball right at your face. Too fast for you to react. What's going to happen? What's going to happen in this situation? What's going to happen when that baseball gets to your face? It's going to hurt. Yes, it's going to hurt. It's going to bounce off your face. It's going to bounce right off your face, come off, and yeah, you're probably pissed off at me. I probably would have gotten fired, okay? At this case. What would the in-class demonstration have been? It would have been fun. We missed out. This would have been something. Yeah, anyway, that's what would happen. Now, let's say instead of that regular old baseball, what if I showed up with a ball made of neutrinos? And I did that exact same thing. I just came up to you, violated your personal space, and chucked that ball of neutrinos right at your face. Right at your face. If that had happened, when the ball of neutrinos hit your face, it would go into your head and come out the back of your head. It would go right through your face and come out the back. Okay? So, would that be good for your face? If a ball of neutrinos went right in the front and came right out the back? Seems like it would be really, really bad. But it turns out it would actually be totally fine. In fact, nothing would happen to you in that case. You would actually be better off being hit by the neutrino ball going straight through your face and coming out the back, because it turns out the main property of neutrinos is that they are, and I'm going to put this right here on the diagram, they are weakly interacting. Weakly interacting. And that means that they do not like to interact with things. And hitting you, that's an interaction. So all of these neutrinos will just go through your face like it's not even there. They don't want to interact with your face. And if they don't interact with your face, then they're not going to hurt your face either. So I'm not saying that it would make a tunnel through your head. It would just go in like a ghost and come out out of the back like a ghost. Like if let's say I was like driving a neutrino car along and I crashed into a wall, the car would continue to go through the wall and I would slam into the wall, and then fall down like a cartoon. The neutrinos are just very, 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 very strange. Okay? Think of them as ghost particles. They go through everything without really affecting them. Okay? And yeah, that's all I really had to say about neutrinos. Positrons. What's something we can say about these positrons? What's something you could tell about these positrons, probably? What's at least one property of them? Somebody's asking me to explain dark matter. I will explain dark matter to you in the chat after all this is done. Give me a second. It's kind of a long discussion. Don't worry about dark matter right now. Okay, yeah, the positrons are positive. What are they, though? It's a little bit weird. Positrons are antimatter electrons. These guys, they are antimatter electrons. And have any of you guys ever heard of antimatter? Probably. Positrons are antimatter electrons. Antimatter is a real thing, and it's not super common, like here on Earth, but the sun is constantly making antimatter all the time, okay? Now, you probably have heard of antimatter in sci-fi movies. Do people usually like to mess around with antimatter in sci-fi movies? Is antimatter a good thing to mess around with? No. Now, why? Why is antimatter a bad thing to mess around with? Why is it so dangerous? Well, it's because of what it is, okay? Antimatter is just like matter, but with all of its properties the opposite, okay? So for every kind of thing we have, every type of matter, so protons, neutrons, electrons, even neutrinos, you can make an antimatter version of it with all of the properties reversed. So a positron is like an electron with all of its properties flipped. Does anybody know what kind of charge a regular electron has? What kind of charge does a regular electron have? Negative. Yes, so a positron is just like an electron, but for example, its charge is positive because a regular electron has a negative charge. Now, someone's asking all of the properties, including mass. What's the opposite of mass? So technically, when I said all properties, I mean all properties that have an opposite. So mass would be something these guys actually had the same. There's no opposite of mass, so the matter and antimatter would have the same mass. But something like charge has two opposite versions. So any property that has two opposite versions like that, the antimatter will have the opposite of what the matter has. And if it's something that doesn't have two opposites, then they just share the same, okay? Now, here's the thing, though. Remember, we said, and we're almost done with this diagram, we're getting to the end, we said that all of the electrons over here, all of the atoms over here, because it was so hot, their electrons fell off. But those electrons are not gone. They're still all over the center of the sun, okay? And so what's going to happen is immediately, as soon as this antimatter gets formed, as soon as these positrons form, they're going to run into, in the environment, a couple of electrons that are just flying by. So a couple of electrons that were just trying to mind their own business, and I'm going to put a little minus on those, will fly by. And what happens is that these positrons and these electrons are attracted to each other because opposites attract. So the antimatter electrons will be attracted to the regular electrons. And does anybody know in a sci-fi movie what happens when matter and antimatter come together? What happens in sci-fi movies when matter and antimatter come together? Yeah, it's usually an explosion. And it turns out that this is one of the few times where sci-fi movies are basically right. The reason you don't want to mess around with antimatter is that when matter comes together with its own type of antimatter, they destroy each other. They completely destroy each other in a process called annihilation. So it's not just explosion, it's annihilation. these positrons and these electrons will annihilate each other, okay? And when they do, they're essentially turning each other into extremely high energy light. So all of the matter and antimatter is destroyed, and what's left in their place is photons of very high energy. What kind of energy is that going to be? What kind of photons are we going to make if they're the highest energy photons? Gamma rays again. And here's the thing, let's see if we can figure this out. How many gamma ray photons are we going to make? Every particle that gets destroyed produces a gamma ray photon. So these two positrons destroy these two electrons. So how many gamma rays are we going to get? How many gamma ray photons? 4. That's correct. So these two positrons and these two electrons, each one of them becomes a gamma ray. So I'm going to pop out here on the other side. I'll just draw one of them, but say 4 gamma, okay? And that's the whole process, okay?